Welcome to this next video in the playlist on group theory. In this video, what we're going to discuss is the concept of a solvable group. Okay, so we'll start off with the motivation and definition. So, solvability is an adjective that you can apply to certain groups. Okay, so if you have a certain group, it will either be given the adjective solvable or it will be given the adjective insolvable. Okay, so it's an adjective that you can apply to groups. And the name is very suggestive, solvable. It originally comes from Galois theory, from the question of when certain polynomial equations will be solvable by radicals. And Galois theory gives a link between field theory and group theory, and it turns out that a polynomial being solvable by radicals corresponds under Galois theory to certain groups having this property of solvability, hence why this property is called solvable. Okay, right, but we're not going to actually be able to give an explanation as to why this is such an important concept for discussing solvability of polynomial equations by radicals in this video. That's a little beyond the scope of this video. I hope eventually to make a playlist on Galois theory in which we'll discuss Galois correspondence and we'll go through all of that. But this video, we're just going to study the property of solvability as a property of groups, rather than actually seeing why should we care about this property, why is it so important. But I will just begin with this statement that it is a really important property that is hugely tied up with the question of when polynomial equations are solvable by radicals. So it is a very important property. Okay, so now what we'll do is we'll actually begin with the definition of a solvable group then. Okay, so the first thing to say is that some people will use a different word to solvable. Some people will use the word soluble, which is just like a shorter version of solvable instead. So if you hear someone talking about a soluble group, it just means exactly the same thing as a solvable group. Okay, so let's actually see the definition then. Okay, so just before we can actually define solvable, I want to firstly define the concept of a subgroup series for a group and a subnormal series for a group. Okay, because in the definition of a solvable group, we are going to need this terminology of a subnormal series. I'm not going to assume that everyone already knows what that is. Okay, so I'll start off with talking about what a subgroup series is so that we can then talk about what a subnormal series is, and then we'll be able to say what a solvable group actually is. Okay, so we're going to be working with some arbitrary group, capital G. It doesn't need to be a finite group, it doesn't need to be an abelian group. Okay, it's an arbitrary group, capital G here. Okay, right. And the first thing I want to tell you about is what is meant by a subgroup series within a group or for a group. Okay, so a subgroup series is an ascending chain of subgroups within a certain group. Okay, so let me draw a picture. It's best to draw a picture for this rather than trying to describe. So you start off in a subgroup series with the smallest subgroup, which is the trivial subgroup. And often you give it a name like G subscript 0. Okay, so 1 here is representing the trivial subgroup, but we're renaming it G0 just so that all the notation fits. And then what we're going to have is that this will be contained within some larger subgroup. Okay, and you don't necessarily have to have it as a proper containment, but it's a bit silly just to have the same subgroup again, okay, as your next one along. So I will put proper containment here. If you don't have proper containment, just get rid of it and go on to the next one, okay? So G1 will be a larger subgroup of G that contains the trivial subgroup, and then you'll continue on up. So you'll go up to G2, and then it will continue on, and it will go on for a finite number of subgroups. So you'll get up to some K, okay, which is some natural number, and GK now will be my new name for the entire improper subgroup, capital G here. Okay, so again, to fit the notation, we rename the improper subgroup G with a subscript here, so that all of our subgroups in this subgroup series are actually labelled the same way. Okay, so G0 is the trivial subgroup, the final GK here is the improper subgroup. Okay, so here, this concept of having this ascending chain of subgroups where you're going to bigger and bigger subgroups of G, this is what is meant by a subgroup series. Okay, so let's draw a little picture of this then. So if we have our group capital G here, okay, and I'll just add a bit of colour onto this because it's getting a little bit black and white here. Okay, so here is my subgroup series, and now let's actually draw a picture. So let's have our entire group, capital G here, coloured in orange. Okay, and now we start off with the trivial subgroups, and let's draw that nice and tinily down here. So it just contains one element, which of course will be the identity. Okay, so we can call that G0, and by the way, of course, we could call the improper subgroup GK to use our new notation in the context of the subgroup series here. Now I'll just colour in the trivial subgroup in pink here, so there's G0, and then all the others are obviously going to be in between these, so G1 will then be a slightly bigger version of G0, so let's say this could be G1, this little extension of G0, slightly bigger. Okay, so I'll colour you in green here, and then you just keep getting bigger, so G2 is another subgroup of the entire group, that's even bigger than G1, so it contains G1. So maybe this is going to be G2 here. Okay, and I'll colour G2 in yellow, I think. So we'll have G2, all of this here. Okay, and obviously it contains all of these subgroups that were previous to it in the subgroup series. And then you just keep going on, so an even bigger one now will be G3 here. Okay, so we'll have G3 coloured in red, like so. And then on this picture, I could have maybe one more shown here. Of course, more generally you can have absolutely loads, but here, in the context of this picture, I'll just draw one more, and this will be G4 here. Okay, so I'll have G4 in vivid purple here, and then GK would now be G5, so in this case K, which is often called the length of the subgroup series, would be 5, so the improper subgroup in this case would be G5, and then you'd be complete. Okay, so we've got this ascending chain of subgroups, and that's the context of a that's the concept of a subgroup series. Okay, so a very simple concept, and you can divide these for any group, capital G. Okay, right, so we're going to go up a step now. So we're going to go up onto the concept of a subnormal series for a group. Okay, and this is slightly more advanced. So a subnormal series is a subgroup series, but when we're talking about a subnormal series, all of these containment, all of these is a proper subgroup symbols, they need to change into is a normal subgroup. Okay, so a subnormal series, I'll draw it out again, would be one like this. Again, you start off with the trivial subgroup here, and then you want a bigger subgroup, but we want it to be the case that the G0 is going to be normal inside this bigger subgroup. Now, of course, in the context of the trivial subgroup, that will always be true. The trivial subgroup will be normal inside any subgroup of the group capital G. But now, going further on, it becomes less trivial. Okay, so when we then go on to G2, I want it to be the case that G1 is normal within G2, etc. So all the way up to the final improper subgroup, I want all of them to be normal in each other. Okay, so again, GK will be the improper subgroup here, and we'll have renamed GK. Okay, so I'll underline that in red. So a subnormal series is a subgroup series where, as you progress up, each of the next one along contains the previous one as a normal subgroup, not just as a subgroup, but as a normal subgroup. Okay, now note, this does not mean that every single one of these subgroups that appears in the subnormal series has to be normal in the entire group. It just means that they have to be normal in the one above them in the subnormal series. Okay, and you might think, but if this one's normal in this one, and this one's normal in the next one, and, you know, normality continues all the way up to G, doesn't that imply that this one is normal in G? But no, it doesn't. Okay? Remember, if you've got a subgroup that is normal inside a bigger subgroup, and then that bigger subgroup is normal inside the entire group, and I'll just write this down. So let's say K is the smaller subgroup, and this is normal inside of H, and H is now normal inside of G, this does not imply that K is normal in G. You cannot conclude that. If K was characteristic in H, the stronger version of normality, and H was then a normal subgroup of G, you'd be able to conclude that K was normal in G, but not just with normality. So you cannot conclude from this that each one of these subgroups is normal in G. Okay, it's not that strong. We just want it to be normal in the one above it, in the subnormal series. Okay, so not all of the subgroups in the subnormal series are normal inside the entire group. That's just a conceptual warning there that people often get confused about. Okay, right. So that's the concept rather. I keep confusing the word concept with context. That's the concept then of a subnormal series. Okay, so we are now ready then for the definition of a solvable group. Okay, so a group capital G is called solvable or soluble. It's a solvable group if, and here's the line, if there exists a subnormal series inside of it. Okay, so I'll write this out again. Okay, so if there exists a subnormal series just like this, where we start with the trivial subgroup and we gradually get bigger and bigger, and every single one of the next subgroups along contains the previous one as a normal subgroup. So we go up to G1, up to G2, up to G3, etc., all the way up to some GK here, which is just my new name for the improper subgroup. So there must exist a subnormal series such that all of the quotient groups that you could form would be abelian. Now, what do I mean by that? Well, if you have a subnormal series, a general subnormal series here within your group, what does that allow you to do? What you can imagine doing is taking G1 and quotienting it out by G0, G2 and quotienting it out by G1, because these are all normal in the next one along. So you can form quotient groups here. You can form G1 quotiented out by G0, you can form G2 quotiented out by G1. You can do all of these quotients. Overall, you'll be able to do K quotients, because you'll be able to do one for each one of these ones. Okay, although there are obviously K plus 1 groups involved in here, the number of quotients you'll be able to do is in correspondence with the subgroups G1, G2, all the way up to GK, so you'll be able to form K of these quotient groups here. Okay, and if we want the group to be solvable, it must be the case that you can find a subnormal series for it, where if you take all of these quotients, if you do Gi plus 1 quotiented out by Gi, it must be abelian. Okay, so it must be abelian, a commutative group. For all I is equal to, we'll have 0, 1, 2, and then we'll go all the way up to K minus 1, and that will cover everything, because if I put in K minus 1 here, I'll get GK over GK minus 1. Okay? So I want every single one of these quotient groups that you can form for the subnormal series to be an abelian group then, if I'm going to give this group the title of solvable. So if you want to work out whether a certain group that you've got, so you've got your favourite group here and you want to work out whether it's solvable or not, you have to search and search and search for subnormal series of that group. And if you found a subnormal series, what you then have to do is form all of the quotient groups that you can for that subnormal series, and you have to ask, is every single one of those abelian? And if the answer is yes, if you can find a subnormal series where all of the quotient groups are abelian, you can then say it's solvable. If you cannot find a subnormal series where all of the quotient groups are abelian, then forget it. You conclude that your group is insolvable. Okay, right, so there is the definition of a solvable group. Now the first thing to say is that this means that all abelian groups are instantly solvable. Okay, so if you've got an abelian group, you can instantly conclude that it is solvable. So abelian group implies that the group can have the additional title being a solvable group. Okay, now why is that? Well, it's really trivial in this case. If you've got an abelian group, then you can form the subnormal series, the trivial subgroup, inside of the entire group. that can be your entire subnormal series. Okay, it's a really boring subnormal series. It only contains two subgroups, and the trivial subgroup and the improper subgroup, but this is a subnormal series because this one is normal inside the improper subgroup. And then when you form the quotient here, G quotiented out by the trivial subgroup here, what do you get? Well, of course you get the entire group back again, because quotienting out by the trivial subgroup has no effect. And the entire group in this case is an abelian group, and therefore it satisfies the definition. So abelian groups are trivially solvable. Okay, this doesn't work in the context of a non-abelian group, because if you just formed this subnormal series for a non-abelian group, then when you took the quotient you'd end up with a non-abelian group as well, and that wouldn't therefore satisfy the definition of being the being a subnormal series which is capable of proving that your group is solvable, because to prove that your group is solvable you need a subnormal series where all of those quotient groups are abelian. Okay, so if you have got an abelian group, you can instantly say it's solvable. What I now want to do is an example of a non-abelian group where we can still conclude that it's solvable. Okay, so we'll take a very, very simple example, and the example we will take is the symmetric group on the set of three elements, S3 here. Okay, so this is a group of order 6, and we know that this group is non-abelian. If you compose two of the transpositions together, if you do it in the opposite order, you end up with a different element. Okay, so it's certainly not an abelian group. Okay, so it's not trivial that this is solvable. So let's instead try and find another subnormal series that we can use to justify why I can give this the title of being solvable, because I can't just use this composition. Sorry, I'm saying composition series. A subnormal series. I can't just use this subnormal series to prove that this is solvable. Okay, right. So what can I come up with then? Well, I will just throw at you the subnormal series which does the job here. So we'll start off with the trivial subgroup, of course, that's always the case, and then we'll have the cyclic group on the set of three elements, which is of course a subgroup inside the symmetric group on the set of three elements. It's the identity plus the three cyclic permutations, and in fact I think what I'll do is just briefly write out the elements of S3 in cycle notation. So of course you have the identity element, which fixes all three elements of the set on which this group's elements very naturally act. Then we'll have the transpositions, and I'll do this in cycle notation. So we'll have the transposition of 1 and 2, the first and second element. We'll have the transposition of 1 and 3, and the transposition of 2 and 3, so the three transpositions there. And then we'll have the two free cycles, so the one that sends 1 to 2, and then 2 to 3, and 3 to 1, and then the other one which sends 1 to 3, 3 to 2, and 2 to 1. Okay, so there are the elements of S3. Now, the cyclic group on the set of three elements, this is the subgroup that just contains the identity element, and then of course the two free cycles, and that forms a nice closed set of elements under this composition law that is the same as the cyclic group on the set of three elements. Okay, and I claim that that is actually a normal subgroup inside of S3. So I claim firstly that this is a subnormal series of subgroups of S3, and also I'm going to claim that the quotients are actually abelian. So let me just firstly justify why it's a subnormal series. Okay, so hopefully it's obvious that the trivial subgroup is going to be a normal subgroup of the cyclic group on the set of three elements. It's always a normal subgroup of any of the subgroups. Okay. Hopefully you're also aware that C3 will be a normal subgroup of S3 because the index of C3 in S3 is 2. Okay, C3 is half the size, half the elements of S3 here. Okay, so if you were to form the right coset partition and the left coset partition of C3 of S3, they'd be exactly the same. Hence why this will be a normal subgroup. Whenever you have a subgroup that is index 2 in the larger subgroup, where it's half the size of the entire group, then it will automatically be a normal subgroup. So that's why we can conclude C3 is normal in S3. Now if we actually do perform these quotients, if we firstly do this one, S3 quotiented out by C3, of course we'll get two cosets there. We'll get the coset of C3, which contains the identity and the two free cycles, and then the other coset that we'll get in that quotient group will be the free transpositions 1, 2, 1, 3, and 2, 3. Okay, so we'll get a group that has only two elements, and of course there's only there's only one isomorphism class of groups of two elements. So I can instantly say that this is going to be isomorphic to the cyclic group on the set of two elements, which is of course an abelian group. Okay, so that quotient will be an abelian group. In addition, this one will just be C3 quotiented out by the trivial subgroup, and of course that will just give you C3 back again, and C3 is also an abelian group, so both of the quotients here are abelian groups. Okay, so I found a nice subnormal series here where the quotients are all abelian groups, hence I can instantly conclude that S3 is an example of a non-abelian solvable group. Okay, so hopefully this initial video has given you a little bit of understanding about the definition and motivation for solvable groups. In the next video, what we will do is we will explore an additional or equivalent definition of solvable groups that works for finite groups. Okay, so this is the most general definition of solvable groups. This is the one to quote if someone asks you what is the definition of a solvable group, because this works for finite groups and infinite groups, whereas the one I'm about to give you will be equivalent to this definition but only in the context of finite groups.